بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is the start of chapter 7, and so far we have already completed with regression, with convex optimization, with statistical learning, and today we are going to introduce classification, which is a very important topic in data science, and we will show the difference between classification problem, regression problem, and I will also present an overview about the most important classification methods, or what we call classifiers. So, of course, the difference between classification and regression is based on the nature of the output. Okay, so in regression, usually the predicted value is, the predicted value will be a value in the continuous domain, okay, which can be any value. And in classification, we usually have a discrete domain, okay, a finite number of possible outcomes. And mathematically, we define the outcomes in a classification problem as a set of possible values from y1 to yk. So here we can have k possible values. And just to have a small example now, if for example we would like to predict the weather temperature, okay, as a value, as a continuous value, so in this case we will have a regression problem. And the question will be, what is the temperature going to be tomorrow? And we will look at the exact temperature value. Now, we can simplify the problem. Instead of having like a real value, we can have, for example, whether it will be cold or hot. And in this case, this is very simple. We have a binary classification. So we have two possible outcomes. And here we have categorical output, not numerical output. So here we have numerical output, and here we have categorical output, and this is why the output will be a finite number of possible labels or possible outcomes. Okay, so there are different applications where we use classification in predictive analytics. Like, for example, in healthcare, and this will be our example today, we can try to estimate the probability that someone would have a disease, for example, a heart disease, given a prior historical data about his health conditions. Okay, so developing some model, of course, if we have a huge amount of data about previous patients and their information, we can develop models that could give us with certain confidence, okay, whether this person would have a heart attack or a heart disease or not, and also what kind of heart disease it's more susceptible to have, or at which degree. So in the financial sector, sometimes it is used to classify people who would like to have a debt, for example, or that they use Visa cards, whether they constitute a low risk, medium risk, or high risk, based on some features of these people. Okay, for example, some people who apply for a loan, they could actually classify whether it's likely to have a high risk for not returning the loan or low risk. And also could be used in marketing, for example, to classify the customer behavior, whether it will be purchasing or not purchasing, and this is similar to the project that we will be working on. Of course, this is a reminder of the use case that we've talked about in the regression lecture, where we had to predict the sales value based on features including the TV budget for advertising, the radio advertising budget, and the newspaper advertising budget. And here we have shown the correlation between the different features and the sales. And finally, we have conducted a regression analysis, and we derived either a simple regression between the television and the sales, or we can have a multi-feature regression that considers all the different features as predictors for the sales. Now, as already mentioned, the type of the sales here, it's numerical value in the continuous domain. It can be a real value. Now, if we consider now our use case today, which is the heart disease prediction, given certain features of a person, we can classify whether this person has a heart disease or not. And there are two ways on how we can classify that. So if you can see here, we can have values that specify the degree of the heart disease. For example, if it is serious, not serious, so we can have multi-labels here. 0, for example, no heart disease. 1, for example, weak, okay, and medium, severe, and so on. Yeah. Or we can also have yes or no, whether it has a heart disease or doesn't have a heart disease classifier. So we're going to consider both. This is a binary classification and this is multi-class classification. And both of them are classification problems because even the output here is a finite number of possible labels or possible outcomes. And here we have the features. Of course, we have data, and this data could be a feature or not a feature. So here the data that we're going to consider is the patient age, the gender, the chest pain type, could be one of 4 possible values, the resting blood pressure, the serum cholesterol, so different type of medical conditions that could help to estimate whether the person is subject to a heart disease or not. And this is a classification problem.
Dr. Feature selection is done under our assumptions, huh?
Yeah, now in this case we're going to have a manual feature selection, but there are techniques that you're going to learn, that will make an automatic feature selection, those who have the highest impact on the outcome.
So it's always taken by the expert of the field you're working on, so?
Yes, there are, sometimes it's visible which are the features. Like for example, if you have the name or the identity, that's not a feature. But considering all these features, you may want to simplify only for those that have the highest impact. Maybe some of the features, maybe they don't have, let's say the weight of the person. It could have an impact, but probably is not as significant as the blood pressure or other type of features. So sometimes when we have a lot of features, excessively huge amount of features, we want to reduce them, to reduce the complexity of the computation of the analysis as well, and developing the predictor model.
So doctor, can't we ask the expert himself of the healthcare that what are the most important features for these?
Usually we do, but among these we can also, the data will tell us what are the most important features. Yeah, the data by itself provides the expertise. Yes. And now we have an issue. So usually you have already learned when we work with convex optimization, gradient descent, or in data science in general, we only deal with numbers. So in categorical data, sometimes you may have non-numerical values or numerical values that are not expressed as vectors. And everything is vector representation in data science computations, right? So we deal with matrix multiplication, with vectors, with tensors. And in order to solve this problem, when we have non-numerical data, we need to convert this data into a numerical representation. And this is what we call encoding. Okay? So we usually do variable encoding. It can be target variable. Sometimes also we can have feature encoding, like male, female. Okay? It's non-numerical value. We can replace it by 0 and 1, for example. Okay? So the encoding is very important, is that to make every kind of feature as numerical representation. And the purpose of encoding to convert categorical variable into numerical format suitable for algorithm processing, enabling integration into mathematical models. And the easiest one is called the label encoding, which is pretty much simple. Now, for example, if I have yes or no outcomes, I can replace no by 0 and yes by 1. And this is a mathematical representation. The target, encoded target, equal to 0 if the target is no, and equal to 1 if the target is yes. But this is just a scalar representation, and usually we deal with vector representations. So the solution to this is to use what we call the one-hot encoding. And one-hot encoding, it converts each categorical value into a binary vector and not a binary scalar value or just scalar value, representing the presence 1 or 0 for absence of the feature. Okay, so for example, if we have the target equal to no or yes, so here we have 1, 0. Okay, so this is index 0 and this is index 1. So you put 1, this indicates 0. Okay, and 0, 1, this indicates the other. Okay, so usually in one-hot encoding, we will have all the values 0 except 1. which represent the index of the predictor, okay, or the output, possible outcome. And this is another vector representation. We can write target no equal to 1, no. So if it is 1, if it is no. Okay, and here because we have a binary classification, so the size of the vector is 2. If I have, for example, multi-class classification, in this case, we can have 3, a vector of size 3, 4, yeah, k, depending on the number of possible outcomes or labels.
Doctor, one question, please.
Yes.
When do you consider an attribute that is not multi-classified? When it has continuous values, right?
Yes, continuous value is regression, is not classification. Yes. So that's a summarization. Yes.
Can an output be 10 values? Yani K can be.
Yes. It can have 1,000 values.
K
It can have 10,000 values.
So K can reach large numbers.
Yeah, in large language models. So it's basically a classification problem. You have a vocabulary of 60,000 values, and you will have the probability of all possible tokens. The highest probability will be most likely 1. Okay. So in real problems, in deep learning, of course, we have a lot of possible outcomes. Okay, so the purpose of label encoding is to convert the categorical data into model readable numerical format. And there are different ways on how we can do this in Python. So if you want to convert a categorical data into just a number, we can use the pandas functionality. So we can have a data frame, and here we can convert the target, which is no or yes, to codes. We can use as type category .cat .codes, and if we print the df, so it will print all the codes related to, depending on the categories available here in the data. If you want to do one-hot encoding, you can do it with scikit-learn. So scikit-learn, it's a library in Python that allows to perform different type of machine learning operations. Okay. So the purpose of one-hot encoding is to convert each category into a distinct binary column or vector, which is crucial for models that do not assume any ordinal relationship between categories. And this is how we do it. So we're going to import one-hot encoder from scikit-learn.preprocessing. So one-hot encoding is considered as data pre-processing step. We do it before starting the training. We don't train unless we do pre-processing. Pre-processing could involve, for example, removing missing values, okay, making amputations or cleaning the data, making one-hot encoding whenever it's necessary. So preparing the data for the training, okay, in the way that the model is going to expect the data shape to be. Okay, so usually you create an encoder, one-hot encoder, sparse output equal to false. Okay, so this is a parameter here. And encoder.fit transform target. So here it's going to look at the target. It contains yes or no, and then we'll convert them into vectors. Okay, so the vector will be of size 2. Whenever, so it's like you have the first column is for no and the second column is for yes. So if you have a no, the first value will be 1 and then 0, and the opposite for yes. So this will be the output of this one. We concatenate the target and we concatenate the df encoded. So this is the encoded vectors.
What's the difference between this and just having one extra column? So if it's no, we give it 0.
Yeah, this is what we call the label encoding. So label encoding is a scalar. But usually when you work with machine learning models, you are doing matrix multiplication and vectors. So it's basically a vector representation of labels. Okay, because you will need to have vectors later on. Okay, not just when you will expect. So at the end you will have kind of like a softmax function, and the softmax function will have probabilities. So the highest probability is the closest to 1. Okay, so this one represent, let's say, a probability. This is the probability that it is a no. Now, when you are going to train your model, you can have, for example, 0.9, 0.1. And of course, we will say this is a no. So the threshold, using thresholding, we're going to decide what is about the class. So it's like will be the output of a softmax function later on.
Yes.
The encoding will help to have a softmax function at the end.
We wouldn't use the scalar encoding.
Scalar encoding.
I forgot what it's called. They wouldn't use it, so it's one hot.
The one hot encoding. Yeah, this is one hot encoding. There are other type of encoders. Huh?
The previous one.
The label.
Label.
Yeah, the label. Yeah, usually it's not. It can be used in simple context, but in real-world application, we usually use one-hot encoders or encoders that will transform the data into a particular vector representation. Okay. So we can also do one-hot encoding with pandas, and here we can use the get dummies, and you provide the df of the target values. So this is very efficient and directly integrates with panda frames, which make it ideal for exploratory data analysis and preliminary data processing. So these are the different ways on how to do that in Python to convert your data into vectors. So this is something always important before starting to train your data is you need to pre-process your data, and I will do an example just by the end of the lecture. So considering this data set, the objective is to classify whether a person would have a heart disease based on the historical medical condition. Now, how can we do classification? There are different classification techniques in the literature that we are going to cover in the future lectures. So today we're going to again review the logistic regression, and the logistic regression is suitable for binary classification tasks, like in our case, yes or no. And if you remember, okay, it's based on a linear transformation of the features plus the application of the sigmoid function. And the sigmoid function, it will convert any value to 0 and 1. Yes?
Doctor, since we have two output vectors, does that mean we're going to train the model on two functions? Yeah, one function for the logistic yes or no output, and the other function for the 0, 1, 2, most likely or none likely. Well,
I didn't understand your question.
We have two outputs.
Yeah, yes or no?
Yes or no.
We will use logistic regression. So first of all, we're going to derive a linear transformation between the features, which are the medical conditions. Okay, then we apply the sigmoid function, and of course we are going to compare the probability that we'll get from the sigmoid function with the expected probability, which is 0 or 1. Okay, and if there is an error, we'll apply backward propagation using gradient descent and convex optimization.
But doctor, my question is, will we develop a model to test yes or no if you will get a heart disease, and another model that will test most likely or from 0 to 4?
Yeah. If you have multi-class classification model, yes, you have to develop a different model.
Yeah, the one model for logistic, we can't put...
Yeah, logistic regression is only for binary. You cannot make logistic regression for multiple classes, of course.
Yeah, you're developing two different ones.
Yes, but there are other ways, like decision trees, which splits the data into branches to make decisions. And this is useful for both categorical and continuous input and output variables. So we will cover all of these techniques. Support vector machine are one of the most popular machine learning techniques, and it's basically based on the concept of hyperplane that best divide the data set into classes. Okay, so for example, if I have two classes in two-dimensional space, I will try to find the hyperplane. In this case, it just will be the line, okay, that will have minimize the distance between the points and the line over here. Okay, and in multidimensional space, of course, we will have a hyperplane of multiple dimensions. We have also random forest, which is an ensemble of decision trees designed to improve the classification accuracy and control over fitting. Neural network, which is based on the concept of neuron, and basically a neuron it constitutes of a linear transformation plus a nonlinear transformation. Logistic regression is one of the examples. I already sent you a video as an introduction to neural network. But in general, we have multiple neurons per layer. So this is one layer, this is a second layer, and every layer will transform the input features into outputs, and this output will be the input for the next layer. Okay? And this is very helpful for the optimization of complex problems that don't have a linear relationship between the features and also the outputs. And KNN is one of the simplest classifiers. It classifies the new cases based on similarity measure, the distance function. So let's get started with the logistic regression classifier. As you have already introduced in a previous lecture, the logistic regression is a statistical method for binary classification and models the probability of the binary response, whether 0 or 1. Of course, we will have a probability. So in order to convert the linear transformation, which is the z variable here, okay, into a probability, we apply the sigmoid function, which will map every value from R, okay, from the real domain, into 0 and 1 domain, which represent the probability. Okay. So there is the concept of logit, and logit is basically the inverse of the sigmoid function. So the sigmoid function, what it does, it will take these values and convert them to 0 and 1. Okay, now this is a probability. So the logit, it's basically, I removed the slide about the logit, but anyway. Yeah, it's this one. Logit of the probability will be just the log of p divided by 1 minus p. And this is exactly the inverse of, it's the inverse of the sigmoid function. So if you apply the logit of this one, you will find it represents the linear transformation of the features. So basically here, speaking it differently, we're going to apply the sigmoid to the logit. Okay, so the logit by definition is the linear combination of the features. It's the log of the probability divided by 1 minus p.
So you convert.
Yeah, that's the definition, yes. Okay, of the logit of probability of y equal to 1. Yeah, it's this linear combination. And we take the logit, we apply the sigmoid function, and we will find the probability itself. Okay. So the sigmoid will be applied to the logit, and we will find a probability of that sigmoid. Of course, this probability will be prone to error when these beta values or the weights are random, and we use backpropagation with the gradient descent in order to optimize over several iterations. I think now you know how to do the process. Okay. The logit by definition, it's the linear transformation of the features. That's it. Okay? And it can be expressed as the log of p divided by 1 minus p. Yes, if you do mathematical computation, you will find that this holds. Okay? You can do a proof. That the inverse of the sigmoid function, yes, yes. Okay, because the sigmoid will be applied to the z value, which is the linear transformation. Okay, so by definition, the logit denotes the linear transformation between the features. And look, yeah, and it makes sense. Look, when we apply the log function will give us values between minus infinity and plus infinity, the standard log. For any value x between 0 and 1. Look at the domain. The log, what is the log definition domain? The standard log. 0 and 1. The log is applied to 0 and 1. You cannot apply the log to other values. And if the value goes to 0, the probability goes to 0, so the log will be minus infinity. And if the probability goes to 1, so we'll have plus infinity. So it's the opposite of the other one. The sigmoid converts any real value to 0 and 1, and the logit will convert to continuous space. Okay?
We need the continuous or we need
Yes.
the binary?
So this is the log y. The log is applied to a value between 0 and 1, and this will give the logit value in the continuous R space. So it's the inverse of the sigmoid. This function is the inverse of the sigmoid function.
But we can calculate it without using the signal.
Yes. No. These are two definitions, but they are reversible. I will send you a proof today about how to go from the logit to the other one. I had slide here, but it seems I skipped adding it. So here, the probability of x equal to 1 given x is just application of the logit, the sigmoid, to the logit function. Now, if you replace this one by the log, okay, let's make it. The exponential of the log is what? It will neutralize.
So they valid.
Yes, so we will have p divided by 1 minus p. The exponential of the log of p divided by 1 minus p. Yes, so exponential will neutralize with the log. We will have p divided by 1 minus p. Just do the equation, you will find it p at the end. 1 divided by 1 plus p divided by 1 minus p is going to be p at the end. Okay? Let me make the proof if I have. We don't have a pen. There is no pen. It's very simple. Okay. So now I will define the likelihood function. And the likelihood is defined as the measure of the plausibility or the likelihood, okay, of a set of model parameters given an observed data. So basically it's given, so it's the likelihood of theta given we have x, or y given that we have x, and it's basically will be the product of all probabilities, okay, the probability of multiple events. So x will be a history of several events. The probability that we have x1, then x2, then x3, then x4. So everyone would have a probability, and to get the whole probability, which is the likelihood, we need to multiply all probabilities with each other. And this will give us the likelihood of an event, theta or y, or an outcome, given a historical value of x. So this likelihood is actually what we want to optimize. But the problem, especially when you have probabilities and you multiply multiple probabilities with each other, what will happen? So the values will be very, very small. Look at here. It can converge to 0. Yes, 1 exponential minus 88. So in order to improve the computational stability, we're going to use the log of that function. And you know that the log of the product of the log, or the log of the product, is the sum of the logs. Yes, it's the sum of the logs. And this is why we have here better margins as compared to the likelihood. Okay, it's not between 0 and 1. It's very, very small values. So they basically do the same thing. So minimizing the likelihood is the same as minimizing the log likelihood, because it's just a log transformation. And it is expressed as the log of fx, the sum from I equal to 1 to n, the log of
previous probabilities.
yes, of previous probabilities. Exactly. So the problem with the likelihood, why we use the log likelihood, is dealing with very small values can lead to computational difficulties. And the log likelihood will use the natural logarithmic of the likelihood, transform the product of probabilities into sums, simplifying the maximization, and enhances the numerical stability of the model. So this is the log likelihood in the context of logistic regression. The likelihood is expressed as the product of the sigmoid applied to the linear transformation multiplied by 1 minus the sigmoid of the linear transformation here. So the log likelihood will be just the same loss function that we have calculated last time, if you remember, in the assignment. Do you remember this one? Yi log of the sigmoid, this is the probability pi, 1 minus yi, 1 minus pi.
Soft max will like.
Yeah, this is the probability of the event.
The proof of the logistic regression.
Yes. So what we've proven as a loss function for the logistic regression is the log likelihood, okay, that we want to maximize in the case of the logistic regression. And we use the minus sign, if you remember, to minimize, okay? So the maximization problem will become a minimization problem. Okay, so basically the convex optimization in logistic regression, it tries to minimize the negative of the log likelihood, okay, which is the cross entropy loss. Same thing. So this is the cross entropy loss, which is the log likelihood of the logistic regression. Different namings, but pretty much the same thing.
Same proof.
Yes. So the cross entropy log loss is just the minus of the log likelihood. Yeah. And the objective here is to maximize the log likelihood. It means minimizing the cross entropy loss function.
So the greater the log likelihood is the less the
Yeah.
cross entropy.
Exactly, yes. So now, how to train a logistic regression model? Now, we've covered all the mathematical concept, which is basically a review what we have done previously. But now training a logistic regression classification model. So usually we'll be given a data set similar to this one. And you need to separate the input from the output, because now we're going to train. So we're going to take the input features, put them into a matrix, and the output features, put them into a vector, and then develop a model that will try to predict the input features based on a logistic regression model. So let's start step by step. So the first thing you have to do is to separate the features from the target. Now, I posted this dataset into rightulab.org CS313 herdata.csv, so you can actually load it from there. And you are going to read it and put it into a data frame. And then, look, initially the data set doesn't have this target. Okay, it only comes with the numerical values of the degree of the herd disease between 0 and 4. So now I want to convert this to either yes or no. It has a herd disease, so I will transform the multi-class classification problem into a binary classification problem. So I create here a new target feature, which will apply a lambda function on the numerical value here. If x is greater than 0, it's yes, it has a herd disease. If it is equal to 0, it will be no.
Based on num? Ah, okay.
Yeah, based on these values, yes.
Ah, okay.
Why didn't we just classify based on number?
Yeah, because this is the target value of the data set. It's a multi-class classification problem. It has values between 0 and 4.
But we changed it to a binary.
Yeah, now I change it to a binary just to make it logistic regression, because if I want to use num, I cannot use logistic regression. But later on, we can use support vector machine, we can use decision trees for multi-class classification problem. But for logistic regression, I need to convert these into yes or no, whether it has a herd disease or it doesn't have a herd disease.
The short one soft max.
Huh?
Also 3 or more, or is it only 3? Soft max.
Yeah, it's more than 2, 3 or more.
So
Yeah,
also
we will use a
for
soft
one
max,
thing,
yes.
okay.
Yes. So basically, soft max is just a generalization of the binary classification. Okay. So here we create the target value by applying the lambda function. And that gives us, so I'm going to select, so for the x, I drop all the output values, num and target, on the x is equal to 1, and y will be just the f target. And here, I have my training data set, which contains the input feature x and the output y. Okay, so usually we use x for the input features and y for the output. This is the standard notation. Okay. The second step, so yeah, I have here yes or no, and I want to make encoding. So we will use one-hot encoding. And the way that we do it here, so we're going to take the categorical data, which is equal to these values, and we will create an encoder, one-hot encoding. So this transforms these features into binary columns. So, and handle unknown categories by ignoring them. So of course, for example, if I take the gender, it has male and female. So it will be converted to a categorical value 0110, okay? So this one, this class or this encoder will do all the work for us. We don't need to do it manually. And look now, if you look at, for example, here we apply encoder, X encoded PD data frame. We apply the encoder to all categorical features. And the encoded dot columns, dot get features, dot get features names output applied on the categorical features here. So look, we will find the two genders. We have 4 values of the second feature. We have 2 values for the third feature, 3 values for the fourth feature, and so on. And this will be converted into values between 0 and 1. So here we have 25 values. So this is a vector that represents the first. So this means this one. So this is the first person, okay? And 1, it means there is, for example, I don't know. Yeah, this is male or female, and then the second one, CP is equal to 1, and so on. Okay, so we create a new data frame that is called X encoded. So look now, I moved from an X similar to this one. All the features now were encoded. I didn't encode only the output, but we also encode the input as well. Okay, we name the new columns using the original feature names to obtain clarity and merge the encoded features back with the non-categorical features. So now we have X encoded, we have Y, and we need to split our data set into train and test data set. So why do we need to do that? So we will train on the test on the training data set, and then we will predict using the testing to see whether we have good accuracy or not. So in order to do that, you have in scikit-learn the train test split, which take the features, the outcome, the test size in percentage. So 20% of the data set will be going to the testing data set. And this is the seed random. So if you want to change from one, change the test data set and train data set for the same split, you need to change the random state over here. Yes?
I've always been confused by this. How do we select how much is the test size and how much is the training?
Yeah, for example, if you have 100, 80%, so 80 will go to the training and 20 values will go to the testing.
Always? Or is that
Yeah, 20%, that's 20%, it's always, okay? To some extent, it can be 19.19%. It depends on how many values you have. Yeah. Sometimes you cannot divide by 20, so you will have plus minus. Yeah. And then we apply, so to train the model, we're going to create a model from logistic regression and using model.fit, apply to the training data and training data, whether it is the feature or the output. So this one, what it will do? It will do the convex optimization. So a training loop, there is a training loop like we did before. It will calculate the gradients, subtract the gradients from the coefficient, and finally update the coefficient. And it will do this several iterations. We can actually specify more features, like for example, how many epochs you want to train, how many steps and so on, the batch size and so on. Okay, this is just the simplest way of training a model. So it will do convex optimization here using the gradient descent, calculate the gradient, update the weights multiple times until it reduces the loss to a certain degree. Okay, doing that, at the end we can have the model.score, which is the final log likelihood. And this means, so how can we interpret this one, 0.86? It means that the model correctly predicts the outcomes at 86 or 87%. Okay? That could be okay, fair value is not, usually we want something above like 95, 96, 99%. So here we can train more, we can add more data, we can change different, for example, training for a longer time. There are plenty of things that we can do over here. So the model.score, it calculates the accuracy.
Doctor, cancel.
Okay. No problem. Yeah.
You missed it by 1 second.
So after completing the training, so we can start doing some predictions. So in order to predict, you can use in Python model.predict. And here you can put the X test. Look now, we're putting a whole vector of, so this is a matrix, not only a vector, because every line is only one feature, okay, or for only one person. So we're going to have several persons, 20% of the data set will be for the testing, and you will have the prediction for all of them. And look now, this is a sample. I make the prediction, and then I will visualize the actual versus the predicted. I will take the Y test and the Y predicted. So look now, I have, this is same, this is same, this is same, but sometimes I can have misclassification. Now the question, what is the performance of this model? Is it sufficient only to rely on accuracy? So accuracy, this is one of the performance metrics. But you will see that there are other ways on how we can observe. For example, how many times it classified yes as a no and no as yes. Yes. هل مثلا الأخطاء اللي عملها في اليس أكثر or more toward the no values? That's another information. Okay? And this will introduce us to the concept of what we call the confusion matrix. Okay? There are different ways on how to assess the performance of the model, like for example, precision, recall, F1 score, and the ROC also. So there are different metrics that we are going to introduce in the next lecture, and these metrics are basically standard for any kind of classifier, whether it is logistic regression, SVM, neural network, or any classifier. Usually we use the standard type of metrics, and basically it's the accuracy, precision, recall, F1 score, and some other metrics that we are going to introduce in order to understand what was wrong. And for example, if you discover that some of the classes has more errors than others, maybe my data is, I don't have enough data for that particular class. Okay, so this type of metrics can give us insights on how to improve the model if there are some deficiencies into the model. Okay, the accuracy is only like an average value, but I don't know what is the variance. Okay, for example, maybe you will find the accuracy of the yes is 90% and the accuracy of the no is 80%. Okay, in this case I need to do something for the no cases, for example, and so on. Okay, so let's stop here today, and tomorrow, inshallah, we're going to introduce how to evaluate and assess a classification model after doing the prediction. Because based on the assessment, you will decide whether you will stop your training or you need to do additional training with some modifications.